separable differential equations. What is a differential equation? A differential equation is an equation with a derivative in it, hence the name differential equation. But what makes it separable? Well, if we have a function that represents a derivative with multiple variables, we're going to choose x, y. If that function is expressed as a product of a function solely in terms of x and a function solely in terms of y, it can be deemed separable. Now, why do we want it to be separable? Because separating the y's from the x's will allow us to solve these differential equations. Now, this is a very specific type of differential equations, and this is the only type that we're going to look at in this course. There's a whole course in undergrad dedicated to differential equations and solving various types and using various methods, but separable differential equations is what we're going to look at in this course. So now, let's just jump right into an example, and then at the conclusion of the video, we'll summarize the steps. So here we have a differential equation, and I identify the derivative notation of dy dx. And on the right, we have dx over y. And if I reformat, I will see that I do in fact have a product of a function solely in terms of x and solely in terms of y. And therefore, this is in fact a separable differential equation. So how do we separate? We're going to get our y's dy's on one side, x's dx's on the other. So let's multiply both sides by y and both sides by dx. So I have this new format here. And to solve this differential equation, we are now going to integrate both sides. We have indefinite integrals here, so we'll need to consider that. But integrating the left side with respect to y is going to be using power rule, so we'll have 1/2 y squared equals, and then on the right side, power rule again, so x squared divided by 2, so 2x squared. And then we're going to put the plus c on the side with the x. We're not going to put it on both sides because putting it on both sides would be redundant, just representing some constant. So we're going to put it just on the x side. Now at this point, we could solve for y to find our general solution. But this problem gives us an initial condition, so we're going to want to find a particular solution. So at this point, if you would like, sometimes solving for y can create some complicated equations when it comes to evaluation. So if you want to find c after you integrate both sides, that is not a bad strategy in some cases. So in this case, let's do that. So I know that when I plug in 2 for x, I should get -2 for y. Here, we're going to get 4 divided by 2 is 2, 4, 8, so c is -6. So if c is -6, I can now take this, substitute in for c, and solve for y to get my particular solution. Again, if I didn't have this initial condition, then I would just have to solve for y right after the integration part. Now, multiply both sides by 2. Then take the square root of both sides. Now, taking the square root of both sides requires a plus minus. But incorporating the plus minus, this does not qualify as a function any longer. So how do we determine whether or not to pick the plus or the minus? It all depends on the initial condition. The initial condition tells us that when we evaluate the function y at some x value 2, we're getting a negative output. So we want y to have a negative output, so we're going to choose the minus. If it were plus 2, so it equals a positive output, then we would choose the plus. But that's how you're going to dictate whether or not to choose the plus minus if that scenario occurs. You're going to look at the initial condition and determine what the output is, and that's how you pick whether or not you have a plus or a minus. So here's our particular solution to that differential equation. Let's jump down to another example. We have dy dx equals x squared times y. The derivative notation dy dx indicates we're dealing with a differential equation. X squared times y, it's clear that we have two functions there, one solely in terms of x, one solely in terms of y, multiplied together. Therefore, this is separable. If we put our y's and dy's on the same side and x's, dx's on the same side, we get this. Integrating both sides to solve this differential equation, we'll get natural log of absolute value of y on the left side and 1/3 x cubed plus c on the right side. At this point, we can define the value of c if we would like. So ln of 2 equals 1/3 0 cubed plus c. So it looks like c is equal to natural log of 2. Now if that's the case, we're going to have natural log of y equals 1/3 x cubed plus natural log of 2. Solving for y. To get rid of that ln requires an exponentiation of base e. So we're going to put base e on both sides. We'll get y on the left side. We're going to get e to the 1/3 x cubed plus ln of 2. Now here, exponent rules. We know that when we take two numbers of the same base multiplying together, we can condense this to 1 by adding the exponents. Knowing this, we can reverse that. So if we see a sum in the exponents, we can split it into a product. So we can say e to the 1/3 x cubed times e to the ln of 2. Now what does this do for us? Well, e to the ln of 2 is just 2. So we can say y equals 2 e to the 1/3 x cubed. And there is our particular solution to this separable differential equation. So now we could have found c at this point down here if we wanted to. Okay, we could have worked there if we just had that c value and then plug in those initial conditions. But if you want to do it from this point, you can. It doesn't matter. But either way, you should get the same result. So whether or not you want to find c after you've solved for y or before is up to you. But both should reach the same conclusion. So now let's, in summary, how do we handle a separable differential equation? First, so identify that you have a product of, it could be actually just, not necessarily just two functions. You might have like dy dx equals x. That's a separable differential equation. I can get my y dy x dx's. Okay, then integrate both sides. So we're just going to have y equals 1/2 x squared plus c. So here's the general solution. It's already solved for y for us. So it doesn't necessarily have to be that second variable there. But if there is two variables, we should identify it's a product of two functions. One in terms of one variable, and the other in terms of the second variable. Again, that's if you have two functions. It could just be one function. We just looked at a quick example there. But most often the questions that relate to this specific topic are going to have two variables in it. Then, once you've identified that you're dealing with a separable differential equation, we want to separate variables. So y dy x dx. So it's going to be obviously more complicated than that, but just get your y's dy's on one side, x's dx's on the other. Or if you're dealing with other variables, so be it. But just separate the variables. Separate variables to match the differential. Remember, the differential is the dx or the dy piece. Once you've done that, integrate both sides. Remember, the integrals are indefinite. So don't forget your plus c. And we'll put it on the x side. We don't need it on both sides. Once we have integrated both sides, solve for y to get the general solution. If you need a particular solution, you can find the value of c either before or after step 4. So we can then, once we find C, we can get our particular solution with using the initial condition. And C value. Okay, so we can find C after the integration or after we've solved for y. It shouldn't matter as long as your algebra is correct. And then we can write our particular solution with that C value. How do we get that C value? We're going to use our initial condition. So there's the steps to solving separable differential equations with some examples.